Now we'll do the temperature composition phase diagrams. So on the left we have the pressure or px phase diagrams. And we're going to switch over now to the tx phase diagrams. And look what's happened to the liquid and vapor phases. Right, on the left, the liquid is on top, the vapor's on bottom because it's pressure. But when we switch to temperature, vapor's on top and liquid's on bottom. Because at low temperatures you have liquids, high temperatures you have vapors. So always just sort of run the axis, max and min, and say, okay, what would I have at high pressure? I'm going to have a liquid. What am I going to have at high temperature? I'm going to have a gas. Okay. So I see nods, so that's good. We have also the XA and YA. We have the vapor line on the pressure curve being below the liquid line. And on the temperature curve, the vapor line is on top of the liquid line. So I'm talking about the red curve in both of these. You see the vapor line is red on the right and the left. And on the right it's on top, and on the left it's on bottom. Okay. We have now on the left we have a particular temperature, and this plot is at a single temperature. So we have a lot of pressures plotted versus composition, but it's at a particular temperature. On the right, we have a lot of temperatures plotted, but that's at a particular pressure. So the one on the right is more common to us because we typically do things at 1 atmosphere. So we've chosen the pressure of 1 atmosphere, and then we plot the temperature behavior of the mixture. Makes sense? So you could have a TX phase diagram, and if it's at 1 atmosphere, then those are all boiling points. The whole curve is a boiling point curve. Make sense? Because you're at 1 atmosphere pressure, and that's what we call the normal boiling situation. So those are all normal boiling points, and it is a function of composition, as you might imagine. You have some things that boil higher than others, and you mix them together, and you get this intermediate behavior. Yes, and so you can't, you got to pay attention to that y-axis, and here it's directly telling you that substance A has a lower boiling point than substance B. You can see that directly off the curve. Those are all boiling points. And let me just do it with the pen so that we can see. So this is the boiling point of pure A right here. TB for A, and this is TB for B. I'll put a B superscript and an A superscript. So A boils at a has a lower boiling temperature than B. Now I've tried to do this for the same, like this is the pressure, the vapor pressure of A. So these curves should go together on this chart. I tried to make them similar. So on the left, you see the vapor pressure at room temperature for A is much higher than B. And so when you take those same substances and then you plot their TX phase diagram, the boiling point for A is really low, the boiling point for B is really high, because B is not as volatile as A. So you got to raise the temperature up higher to get it to boil. Yeah, I like the TX better myself. Yeah, it just makes more sense to me. I like to pick 1 atmosphere and look at my temperatures. They're all boiling points if it's at 1 atmosphere. Okay. We still have the XA and YA business. So you see here at 1 atmosphere, this is the boiling point at room temperature for this liquid mixture. And the composition of the vapor is over here, and it's enriched in A, which is the more volatile component, which is what we would expect. Did everybody follow what I did? Just walk you through. We're at 1 atmosphere. That's the boiling point of that XA liquid mixture, and the vapor pressure is enriched in A, which is the more volatile substance. Okay. So over here, that mixture, this is all at 1 atmosphere, and so we've got that same mixture. We come up here, and here's room temperature, and so it matches, right? It's boiling at room temperature. Here's room temperature over here. Boiling at room temperature. Here, boiling at room temperature. Everybody see it? And here's the composition of the vapor, enriched in the more volatile component. The more volatile component has the lower boiling point. Yes? So if we were to take this substance and warm it up to room temperature, at this point it would start boiling, and this would be the vapor. If we condensed it, it would have this composition. So that would be a simple distillation. So one-step distillation. We come up, boil the mixture, collect the vapor, condense it, and we have it enriched in A. Is there anything on here that you need clarification on?
So on the right, at boiling point, you have almost D1% A.
Yes. Yeah, it's kind of weird. So you put in it's 30% A. So you have a 30% A in your pot down there, and you boil it and collect it, and it's over 50% A. Yeah. So that's pretty good. And this is the distillation setup. So this is a cool image that we got in my lab. I saw an email advertisement for this infrared camera that attaches to an iPhone. Okay, and so I well, that's kind of cool. And so then iPhone 5 is an old one, and so it was $200. Yeah, I mean that's really great, pretty inexpensive, and you get pictures like this. So I set up my fractional distillation and took infrared pictures of it, and you can see the temperature gradient going up the fractioning column. And down at the bottom it's really hot, and it cools as it goes up, and you get this condensation and reboiling all the way up the fractioning column. And then at the top you hopefully have just one volatile substance, the most volatile substance, condensing, and you'll see the temperature of that condensate be the boiling point of that condensate. And down at the bottom you got a higher boiling point. You have this temperature gradient. The bottom has the boiling point of the mixture. The top has the boiling point of the condensate. So that's the condensate temperature at the top. We have, here's the condensate if you were to collect it. Oh, settle down. Then you have the fractioning column, and the still bottom is at the bottom, and then I also call it the pot. So I put that in as a vocabulary word, but it's really slang. It's just, what do you have in the pot, and it's just what I've always called it. So I have to tell you the vocabulary that I use, just so that you know what I'm talking about in class. So they have the still bottom or the pot, and the pot boiling temperature, and so that's going on. That's what's going on with fractional distillation. And I know every one of you have done it. You're chemistry majors, or chemistry graduates. You have degrees in chemistry. You've done distillation, and so this is what's going on in the phase diagram for distillation. So we take this substance. In this case, B is the more volatile substance. We boil it. So the pot's boiling here. And they've got in this particular case, a huge separation between vapor and liquid compositions. So it goes up the flask and condenses. So this vapor has gone out of the still bottom and up the fractioning column until it cools down a little bit and it condenses on the wall. So it condenses on the wall, or the stainless steel chain, or glass beads, or whatever you have in there, and it starts to drip back down. Well, as it's dripping back down, the temperature's going up. And this is enriched in the more volatile compound, so it has a lower boiling point. So it doesn't have to go all the way back to the still bottom to boil again. It comes down a little ways in the fractioning column, and then it can boil again. So it's boiling in the fractioning column. And it's enriched in the more volatile component, and it goes even higher in the fractioning column before it condenses. So it drips down a little ways. Notice this is a lower temperature, and so it boils at a lower temperature in the fractioning column, and even more enriched vapor goes higher in the column, and it condenses again. And if we just did this in 3 steps, we'd have mostly B. So this would be very easy to separate if we had this kind of phase diagram after 3 theoretical plates. We'll talk about what the plate things mean in a second. The one on the right, you see those curves are closer together, and so we would need, in this particular case, 5 theoretical plates to separate them. Do you remember taking instrumental analysis and talking about chromatography and how easy you could separate those compounds by running them through a 30-meter GC column? Well, do you remember what the theoretical plates were in those separations? for those columns? Somebody just off the top of their head remember when you calculated the number of theoretical plates for a particular column separating two substances? It's typically when you had two substances that were trying to coelute and you figured out the resolution of that column and how many theoretical plates you would need to separate those, say to baseline resolution. Anybody?
We did it, but it's been a while.
It has been a while. The theoretical plates for gas chromatography are in the tens of thousands. So you could separate compounds that have, very similar boiling points. I mean, actually immeasurably close boiling points. You can still separate them in gas chromatography. Distillation, you're probably not going to get butane away from isobutane. Chromatography, that's easy. But we use that term theoretical plates. And I asked my professor, what's a theoretical plate? He said, well, it goes back to distillation, and they used to have bubble plates. And nobody uses bubble plates anymore. That's what he said.
They do some little thing.
Yeah, right? And what does he mean by that? He means nobody in academia uses bubble plates anymore. But you go off the campus and you go over to a refinery and they use bubble plates. And we'll see a bubble plate here. So this is basically what I just did with my pen. These are bubble plates and they're still used in refinery separations. So the vapor doesn't just go up the column and condense on the glass wall and come down. It actually has to bubble through the next layer of liquid. So this fractioning column actually has little plates that hold on to the liquid that's condensed. And if that liquid doesn't want to boil at that temperature, it can make its way back down to the pot. So like if you had some sort of temperature bloom and it blew a lot of hot vapor up too high in the column, that column will come back to equilibrium or steady state, and that non-volatile liquid will flow back down into the pot, and the more volatile liquids will go higher and higher. And so this is how they do separations in industry. You have the temperature gradient, hot to cold. You're putting an enormous amount of electricity into the heating elements at the bottom. Most often this is crude oil. So they're heating up the oil at the bottom, and all of those volatile components are going up through the bubble plates. So let's zoom in on the bubble plates. This is the sort of side cut view. The vapors coming from the pot have to boil and bubble through this bubble plate. So this is the bubble plate, and this is the bubble cap. And if those volatile vapors are still volatile at that temperature, they'll go through the next one. But what if they're happy here? What if this is the right temperature for condensation? Then they condense. And yet there's this temperature gradient, so the more volatile ones will leave, but the less volatile ones will stay. If you got some really heavy ones, they'll flow back down towards the pot. They'll go into the previous plate below. So you get a pretty steady state with these fractioning columns, and the different boiling point cuts will come off. And so you might have kerosene or diesel fuel coming off at this temperature, and gasoline coming off at this temperature. And way up here you'll have the petroleum gases like butane and propane coming off. So this is how it's going. And this is the zoom in. This is the bubble cap plate. You see all the little bubble caps here. And this is the little bubble cap screwed onto the little volatile escape hatch. So the vapor comes through this and it has to go down into the liquid to get out of the bubble cap. And so it bubbles out of those caps. So we still do use bubble plates. And this is an example of one. So over on the right is a fractioning column. You can see how tall it is. You can imagine how that temperature gradient is. There's probably even insulation inside some of those shells so that they can control the temperature and set up a really smooth temperature gradient. And then you have the taps coming off. You've got maintenance and sampling platforms and so on. So whenever you drive by a refinery and you see all of these tall columns, you're looking at fractional distillation. They're called fracking columns or frac columns, frac towers. Yeah, it's different than fracking an oil well, totally not even related. So, but this is fractioning columns. So here's a little scheme that I saw on the website. It's given down below, where you've got up there gas vapors, naphtha, which is like a solvent that we use. you can probably burn it as well. Kerosene and diesel. And then you have heavy and light gas oils that are cracked. You have a catalytic cracking unit called a cat cracker. So catalytic cracking units that will take oils that have a high double bond equivalent, so lots of double bonds, and they'll add hydrogen to that. And so they'll make a more saturated molecule, which would be a more volatile molecule, which would go into the gasoline stream, which is your revenue driver. And so you can only sell so many heavy oils as greases and lubricants and things like that, or heating oil. It's much better to get into the gasoline market where you can sell it for a higher dollar per gallon, and the demand is huge. And so if you can make a catalyst that will get 1% more yield of gasoline versus all of these others, it's worth billions of dollars. And if you're an inorganic, Wilkinson's catalyst is one of the famous ones, and he got the Nobel Prize for that by increasing the percentage of gasoline over diesel by just a few percent. It's a rhodium catalyst. So that's high dollar science. So now let's talk about distillation with the TX phase diagrams. And here we have a situation that's difficult to separate. Notice it's a strange phase diagram. It doesn't go straight from A to B anymore. There's a bump in the middle. And we showed this with the PX phase diagram. We had that that was the carbon disulfide and acetone, which had a pressure maximum. And I drew the vapor curve on there, and they pinched at the top, and I called it an azeotrope. This is the same kind of thing, only this is a TX phase diagram showing an azeotrope. So up here at the top, if we were to take B and boil it, we get up here, this would be the boiling point of B, and this blue line is the vapor composition. And notice that the liquid and the vapor compositions are equal. So XA is equal to YA. And that's the definition of an azeotrope. So zeotropic behavior is when they're different. So non-zeotropic behavior is an azeotrope, where XA and YA are equal. The most simple way to think of these phase diagrams is just to divide them in two. So in this particular case, the thing with the high boiling azeotrope is that's the least volatile substance. The high boiling, it's got the highest boiling temperature, so it's the least volatile substance. Okay. And so if you were to just take this phase diagram and divide it right here at the azeotrope, you would just draw a vertical line if you wish. Then you've got two phase diagrams, the one on the left and the one on the right. And so if I start here at A and I boil this substance in a fractioning column, then something that's enriched in A is going to condense and reboil and condense and reboil. So I could collect some of that excess A as in my collection flask, and the pot concentration would move to the left. It would move towards the azeotrope. And so this, if I kept boiling this, I would boil off all the excess A, and this would creep up until my pot boiling temperature was the azeotropic boiling temperature, and my condensate would stop coming out. And you see this. You see the dripping over here in the condensate, and if you were to do a Raman spectrum or some kind of a analysis, you'd have pure A coming over because you have excess A. You're past the azeotropic point. You have more A than the azeotrope. So A would be coming off in the condensate, and if you were to measure the pot composition, it would be moving towards the azeotrope. As it gets closer and closer to the azeotrope, you have less excess A. And so the dripping rate in your condensate flask would start to slow down. And eventually your temperature would move, up at your condensate temperature, and it would move from the it would move from this temperature here, which would be the condensate temperature for A, and it would rapidly jump up to this temperature. Because the pot is now boiling the azeotrope, and the azeotrope would start to come over. And so that's when you would swap out your collection flask, and you have, removed all the excess A that you had. You can set that aside. But now you're just distilling the azeotrope over. And so you can distill the azeotrope for a while, but then you don't ever want to run anything dry. And so you could clean up the azeotrope this way, but you could never separate the azeotrope. You could never get B away from A. You would only collect that high boiling composition. What about if you're on this side, you have excess B? So if I start over here and boil it, then my condensate temperature would be right there, and my pot would move towards the high boiling azeotrope. Does everybody see that? You really have two phase diagrams. If you have less A than the azeotrope, that just means you have excess B. And if you boiled that, B would come over into the collection flask. If you're on the far right, if you're past the azeotropic composition, you have too much A, and A would be collected if you boiled it. So whatever's downhill on a TX phase diagram is going to come out in the collection flask. So I would like you to be able, if I dropped you anywhere in this diagram, to tell me what's going to go on if you boil. Okay. So if I put you here, like if I just drop you right there, what would happen if you boiled that? You just narratively tell me, okay, I would collect A in the collection flask, and my pot would move towards the azeotrope. And eventually my azeotrope would start to come over. If I dropped you on this side, B would come off in the collection flask, and the condensate temperature would be the boiling point of B. And that would last for a while, but then the excess B would be gone, and I would be at the azeotrope. Okay, it's 9:50. That's a good place to stop.